Okay, so in 18.3, if you go back and check that out, we saw that if a fluid accelerates, okay, if you remember, right, there was this tapering, right, and the fluid going in like that. If it was accelerating, meaning the velocity over here, say v2, was higher than v1, okay, so v2 was higher than v1, then it was accelerating, and if it's accelerating, then there has to be a force applying, a force causing that acceleration. And so the force over here, there needed to be a force over here onto this section over here, which meant that the pressure over here is higher than the pressure here. Okay, so the pressure must be greater in the wide part. So now the thing is, let us now look at how does pressure relate to flow speed. Okay, so if we consider this figure over here, we have a few things that we need to take note of. The first is the cross-sectional areas between point 1 and point 2. It's larger here, smaller there. There's a velocity 1, a velocity 2. There is this volume of fluid that moves from here and basically comes out over here, okay? And you see that it becomes missing, okay? Missing. So we consider this volume over here that moves and comes out there. We also consider height, a height difference. Okay, so this point over here is at a certain height y1, and this point here is at a certain height y2. Okay, so we consider the area, the speed, the pressure at 1, and the height. So we consider that for both of these guys, and the question now is, how does the energy of this system change? Okay, so remember, we want to relate pressure to the flow speed. How does pressure change the flow speed? Okay, so to try to answer this, let's look at the energy. How does the energy of the system change? Well, remember this equation from chapter 9. The change in energy of a system is equal to the work done on the system. So let's start off in this video by just looking at the change in energy, and in the next one we'll look at the work. So remember, we said that this mass over here becomes missing because it basically moves through the system and it comes out over here. But now take note here that, so the only thing that's changing in this system is this mass over here. It becomes missing and then it gets added over here. Okay, this whole section, that whole section there, remains the same. There's no change in anything for this section. There's no, everything in this section remains the same. Okay, so it says here, because the mass of the fluid between points 1 and 2 doesn't change, the only forms of energy we need to consider are the kinetic and potential energies associated with M1 and M2. Okay, so let's look at, when we consider this change in energy, let's look at change in kinetic energy and change in gravitational potential energy. Okay, but it's only of these two masses because they're the only things that change. Okay? Alright, so this is pretty straightforward now. So the change in kinetic energy of the system is the kinetic energy of V2 minus the kinetic energy, the kinetic energy of M2 minus the kinetic energy of M1, which gives us this. And the change in gravitational potential energy is the potential energy of mass 2 minus the potential energy of mass 1, which gives us this. Okay? So this left-hand side of the equation then becomes delta E is the change in kinetic energy plus a change in gravitational potential energy, which then equals this. Okay? Kinetic and potential. Alright, so that's Good enough for this one. We looked at the change in potential energy. The next one we're going to look at the work.